Okay, we're still in 2.4, polynomials and rational functions, and now we'll move forward to our next objective for this section, which is being able to graph and identify properties of rational functions. So what are rational functions? Well, we define a rational function, f of x, as a quotient of two polynomials, n and d, n of x, d of x, for all x such that d of x is not equal to 0. So you could sort of think of your rational function as n of x over d of x, where each one of these is polynomials. N of x is a polynomial, d of x is polynomial. And d of x can be 0 here, right? Because it's in the denominator. That's the key. So, for example, if you take n of x to be the polynomial x plus 5, and d of x to be the polynomial x minus 2, then f of x equaling x plus 5 over x minus 2 gives us a rational function. Notice this is a rational function whose domain is all real values of x, with the exception of 2. And why is that? Well, again, for the reason that we just said in the definition, the denominator can't be 0. If the denominator is 0, then we have division by 0 here, which is undefined. So this cannot be 0, so we have to be careful. Our domain is restricted to all numbers except 2. Okay, let's talk a little bit about vertical asymptotes now of these rational functions. So as you read, x values at which the function is undefined represent what are called vertical asymptotes to the graph of the function. What is a vertical asymptote? It's a line, a vertical line, of the form x equal to k, which the graph of the function approaches but does not cross, as in this example here, x plus 5 over x minus 2. So notice in this example, the graph of the line x equals to 2, right, k is 2 in this case, is a vertical asymptote. This vertical line, x equal to 2, is a vertical asymptote because, well, the value of x equal to 2 is makes the function undefined. So that's what gives us the vertical asymptote, number 1. Number 2, visually, our graph, as seen on the calculator, is going to get really, really close to x equals to 2, to this vertical line, without ever hitting it. It's never going to cross it, it's never going to intercept it, but the values of our function will get closer and closer to this vertical line here. It will just never ever hit it. Okay, so that's what a vertical asymptote is. On the other hand, we have also horizontal asymptotes, which are just horizontal lines, right? Lines of the form y equals to k, which the graph of the function approaches as x approaches positive or negative infinity. So what these horizontal asymptotes tell us is essentially how our function behaves in the long term, right? As it goes towards positive infinity and as x approaches negative infinity. So what's happening to our function in the long run? That's how you should think about it. So for example, in the graph of x plus 5, right, that's what we have here, again, our function x plus 5 over x minus 2, this line, y equals to 1, the horizontal dashed line here, y equals to 1, is a horizontal asymptote. Why is that? Well, that's because as x becomes infinitely large, as it gets bigger and bigger and bigger, this fraction, x plus 5 over x minus 2, is essentially going to reach the value of 1. Okay, we'll discuss this further when we talk about limits later in our class. For now, it might not be obvious to you, but just plug in a really large number, like x equals to 10,000. Then you're going to get 10,005 over 9,998. Right? And if you do this on a calculator, you'll see that this gives you about 1. And as the numbers get larger and larger, maybe next you pick something like 1 million. Right? Then you will get 1,000,005 over 999,998. So that's also going to be close to 1. And the same thing happens if you pick really, really large negative values of x and plug them into this rational function. You're just going to get closer and closer to positive 1. So do this just to convince yourself that it's true. Okay, so let's see. Here's the generalizations about the asymptotes that rational functions have. For the vertical asymptotes, you have two cases. Suppose that in your function, right, which is n of x over d of x, numerator over denominator, suppose that they have no real 0 in common, then the line x equal to c is a vertical asymptote as long as that c makes the denominator 0. So x equal to c is the input such that the denominator becomes 0. So for example, x plus 5 and x minus 2, notice these two polynomials have no real 0 in common. They do not have any real 0 in common. You can't cancel or factor anything out. The line x equal to c is the vertical asymptote, then if d of c is equal to 0, notice that d of 2 is 0 because 2 minus 2 here will give me 0, right? D of 2 will give me 0. That's why x equals to 2 is the vertical asymptote. We put VA for vertical asymptote. So one case is going to be exactly what we've already looked at. The second case is if they do have something in common. So if n of x and d of x have one or more real zeros in common, then you have to cancel out those linear factors and apply case 1. So here's an example. If you have f of x equals x plus 5 times x minus 3 all over x minus 2 times x minus 3, notice these now have real zeros in common. 3 is the real zero, or you could think of them as terms in common. So you have to cancel them out, and then that will get you back to case 1, right? And in this case, I chose the example to be the exact same rational function as in case 1 after you cancel out. But it doesn't have to be, right? It could be anything. Okay, so that's the story on vertical asymptotes. On horizontal asymptotes, you also have 3 cases that the book goes through, which I recommend you just remember. So you have 3 cases. Later on, again, when we do limits, these will show up again and you'll think about them differently. But for the time being, remember that if the degree of the numerator, right, you have n of x and d of x, if the degree of the numerator is less than the degree of the denominator, then y equal to 0 is the horizontal asymptote. So for example, if you have f of x equals x minus 1 over x cubed plus 3x squared minus 5, right? Then notice that the degree of the numerator is less than the degree of the denominator here, right? Therefore, the horizontal asymptote is y equal to 0. You can grab this on your graphing calculator and convince yourself that it's the case. Case 2 says if the degrees are even, then y equals a to b is the horizontal asymptote, where a and b are the leading coefficients of the numerator and the denominator respectively. So the example that we just did earlier, x plus 5 and x minus 2, the a and b were these coefficients. They were the leading coefficients of the top and the bottom respectively. This was the a and this was the b. They both happen to be 1. Therefore, the horizontal asymptote happened to be the line y equals to 1. So as another example, if I gave you f of x equals 2x plus 3 over x minus 4, the vertical asymptote would be y equals to 2 over 1, right? You take the leading coefficients, and that would be 2. So that the horizontal asymptote would be 2 there. Finally, if the degree of the top is bigger than the degree of the bottom, then there is no horizontal asymptote. So as an example, take y equals x squared over x minus 1. There is no horizontal asymptote. Okay, and one last thing that I wanted to show you here in this video is bounded. When is a function f bounded? It's bounded if the entire graph of f lies between 2 horizontal lines. So if you can fit the entire graph between 2 horizontal lines, maybe something like this. Okay, so this is an example of a function that's bounded. Well, the only polynomials that are bounded are the constant functions, but there are many rational functions that are bounded. Okay, and your book goes through some examples, so take a look at the examples in your textbook for those. For the constant function, it's a very easy case. If you just grab the constant function y equals 3, let's say, then that's obviously bounded because the entire graph can be put between 2 horizontal lines, right? So for example, y equals 4 and y equals 1 or something. Okay, we could think of that. So think of the definition of bounded and look at those examples in your textbook.